In this video, we're going to be talking about the Flash ADC, which is one of the fastest analog to digital converters. The Flash ADC is made just like the one I designed here, which is a 3-bit ADC, which means we convert an analog signal into a digital one that has 3 bits. To remind you from the previous video when I was introducing analog to digital converters, when we wanted to see how many voltage levels we can have with a certain number of digits, we used this formula. 2 to the number of bits equals the number of voltages. Okay. So here, since we have 3 bits, if we substitute in the formula from above, we can have 2 to the number of 3, which equals 8 possible values, 8 possible voltages. So that's 0, 1, 2, all the way up to 7. So how this ADC works is you have analog voltage on the left side, both V reference, which is here Vref, and V input, which is V in. That means that it can be anything. We could have 8 volts, but we could have 747 volts or anything else since it's analog. For simplicity, we're gonna take that the Vref is equal to 8 volts, because you'll see later that it will be much easier like that for the calculations. So let's start with Vref. As you can see, there are multiple resistors below it that are all equal. In particular, there are 8 resistors, so in general, for a flash ADC, the number of resistors will be 2 to the number of bits. So number of resistors equals 2 to the number of bits. Okay, so this is done on purpose to have a voltage divider after every resistor, so we can have different voltages everywhere. If you don't know what a voltage divider is, make sure to write in the comments so I can make a separate video on that. Okay, so to see how voltage changes down the line, we're gonna start analyzing it from the bottom up. Let's start with this node right here, which we called V1. From a simple circuit, a voltage divider is this right here. Okay, so let me draw a simple circuit. Okay, we have 2 resistors in series. We're gonna call this R1, R2, Vgen. And the voltage across the second resistor we're gonna call V2. So here is the same thing as above, because below here we have a ground, and also above we have a ground, and above we have a bunch of resistors in series, as you can see right here. Okay, and also here we have a resistor in series. So to draw the equivalent circuit from above, we can write it like this. So you can see that V generator from above, from here, is just the V reference here, okay? And the first resistor here is just the 7 resistors put in series. Since you know that if we sum multiple resistors that are put in series, we can represent them as one resistor. So for example, if we have 2 resistors like this, 1 ohm, 1 ohm, is the same thing as writing one resistor that has 2 ohms. It's identical. And the second resistor here is just the last resistor in the circuit, which is this one right here. Okay, so since the voltage divider formula we have to use the voltage divider formula. So we have right here V1 is equal to R times 7R times Vref. Sorry, 7R plus R times Vref. Okay. I can write them all as R since they have the same value. As you can see here above, they are all named R, R, R since we want them to have the same value. Okay, so this right here is equal to R divided by 8R times Vref. These cancel out, so we have 1 divided by 8 times Vref. And since we have Vref equals to 8 volts, as we said before, so this is equal to 1 divided by 8 times 8, which is equal to 1 volt. So we have that V1 equals to 1 volt. V1 in particular is this node right here, okay? So we're just gonna write here 1 volt. If we take the node from above, V2, okay, we can see that the voltage right there is equal to V2 equals to 2R divided by 2R plus 6R times Vref, using the same exact reasoning. Since below we have below this node right here we have 2 resistors, and above we have 6 resistors, and that is the reason why we use this formula from the voltage divider. So this is equal to 2R divided by 8R times Vref, which is equal to 2, this cancel out, 2 divided by 8 Vref. Okay, so if we continue with the same reasoning for every node in the flash ADC, we'll have V7 is equal to 7/8 Vref. As you can see, V1, this right here, is the smallest one, and V7 is the biggest one. So that's why we call our V7 our most significant bit, MSB, and V1 our least significant bit, LSB. So Vref is something that stays there and is stable, and Vin is what we call an analog voltage. Is the analog voltage that we actually want to represent as a digital voltage, and the little triangles on the right are called comparators. These triangles right here are called comparators, okay? And we use them to compare Vin with Vref. Okay, so how they work is that as you can see here at the top part of the triangle there's a Vin, and at the bottom one there's a Vref. Okay, so they work in this way. If Vin is bigger than Vref, then the output of the comparator will be 1. If Vin is smaller than Vref, then the output of the comparator will be 0. Let's take an example now to finally understand how everything works. I'm gonna copy and paste this below for more clarity. Okay, so let's take that Vin equals 4.2 volts, and this is the voltage we want to convert. We want to represent this as a digital voltage, and let's say that Vref is equals to 8 volts. Okay, so we can also write above 8 volts, and we can write 4.2 volts. Okay, now going to this design, we can see that if we want to compare the Vin and Vref, we can see that here, since they're at the part of V in, there are no voltage dividers, so we have everywhere 4.2 volts. Okay, it's the same below, but here we said we have 1 volt from the formulas we calculated until now, then 2 volts, 3 volts, 4 volts, 5 volts. Okay, so we can notice that here, let's zoom in a little bit, we have 4.2 volts versus 4 volts. Now we said that if V in is bigger than Vref, output is 1. So here we have 1. Okay, here we have 4.2 volts and 3 volts, which is also 1. So is everything below. But above we have 4.2 volts compared with 5 volts, so it's 0. And everything above is 0. Okay, now as you can see here on the right, I wrote a priority encoder, which means that the flash ADC will give some of the outputs a priority and will choose just one of them, since it can choose everything, since we want to convert just one voltage. In the flash ADC, it will always choose the highest one, which is in this case is the one right here. Okay, it will take that one, and the encoder knows that the output corresponds to the number 4, and we will get 1 0 0 in the output, which is 4 in binary. So we successfully managed to convert an analog voltage, which is 4.2 volts, the one right here. We managed to convert it into a digital one that represents 4 volts, and we did it. Now you might be confused why it's not the identical number, but one is 4.2 volts and the other is 4 volts. Because when converting from analog to digital, there will be an inevitable loss of information, and in this case it's gonna be not getting the exact same in the output. But we're okay with that, because most of the time working with digital signals gives you many advantages that outweigh the disadvantages, and we don't mind in this case because it's a very little loss of information. That's it for today, and hope you enjoyed this video, and see you in the next one.